going to go through the chapter on integral equations today, and I'm going to go through it fairly quickly because I don't think it's as important as some of the other chapters, but I think it's worth knowing about. Also, I just noticed today that I had forgotten to assign homework. So I've assigned 8 problems due not Friday of this week, but Monday. Sorry for being so slow. All right, so let's see. Once again, we've got this pointer, which is just my finger here. If we have a first order differential equation and we integrate it, we then get an integral equation. And the integral equation then has boundary conditions, namely u of a is given. It's this thing on the right-hand side, and then the value of u at any other point, well, it's given by doing the integral. So it's easy to transform a first-order differential equation into an integral equation. You just integrate once, and then you're there. You can think of p of y as a kernel, and then this piece here as an inhomogeneous term, and in a sense you've got an eigenvalue hidden here, and you can recover the eigenvalue if you want by you could just, for example, multiply the whole equation by lambda, and then you find the eigenvalue as lambda p and lambda q and lambda u of a. What's less trivial is, or more involved, I should say, is transforming a second order differential equation. And here, the first thing we do is we use Cauchy's identity. So this is we're going to have to integrate twice to get turn a second order differential equation into an integral equation. And so the double integral is on the left-hand side, but Cauchy figured out long ago that you could rewrite that as a single integral. And this is a special case of his formula for an nth order integral. So integrating f n times is the same. You can get away with integrating it just once if you integrate something a little more complicated. And I think maybe what I'll do is show you, I think I'm going to do some of the exercises in chapter 8. And so let me, why would the chalk be way over here? So let's look at deriving 8.3. And it's actually pretty easy to derive. First of all, you differentiate it with respect to x. And if you differentiate with respect to x, what you get is ax f of y dy equals ax f of y dy, and that's obviously true. So this equation is correct. Notice there was a subtle point here when you differentiate. You differentiate with respect to the x inside the parenthesis here, you obviously get the left-hand side. But if you differentiate with respect to the x that's the upper limit, what you get is x minus x f of x, and that's 0. So that's why that didn't appear. So you get this equation. So that's true. So that means that equation 8.3 has to be right apart from a constant, because it has the derivative of the left-hand side is equal to the derivative of the right-hand side. So 8.3 has to be right apart from a constant. Well, the constant's 0, as you can see by setting x equal to a. If you set x equal to a, both sides are 0, and so the constant is 0. So the next thing is to show why it is that if we integrate this equation, let's see, what equation are we integrating? Yes, we're going to integrate this equation, and I want to show you that if you integrate this equation using Cauchy's trick, what you get is this with a certain kernel and a certain inhomogeneous term. So this is a particular type of integral equation. It's actually a Volterra equation of the second kind, an inhomogeneous Volterra equation of the second kind, named after Vito Volterra. So if you integrate this equation once, what you get is u prime of x is equal to integral a to x dy p of y u prime of y plus q of y u of y plus r of y. Almost sounds like Uruguay. But anyway, plus u prime of a. So that's the first integral of the second order ODE. And now what you do is integrate again. And so if we integrate again, what we have is u of x is equal to a to x, that integral, now dz of the integral a to z dy. Now all of this stuff, which is py, let's see, everything's a function of y there, so I think I'm going to use a shorthand. Pu prime plus qu plus r plus u prime of a. And then we have plus u of a. So that's the extra constant of integration. Now we've got a double integral of the Cauchy form. And so if we apply Cauchy's identity, what we have is integral a to x dy, x minus y, pu prime plus qu plus r, and then the extra terms are x minus a, u prime of a, plus u of a. So the Cauchy trick gets us from there to there. And now what we do is we integrate by parts on this u prime. And when we do that, what we get, oh, actually, I can stay over here. I can just raise this. They thoughtfully put rubber, I don't know what to call them, but anyway, rubber stoppers up there, and they stop the sliding blackboard from slamming into the aluminum frame. So what we get now is u of x is equal to integral a to x dy, and again pu plus x minus y minus p prime u plus qu plus r, and then we have plus a boundary term, which is x minus y pu. I'm leaving out the y dependence. Ax plus x minus a u prime of a plus u of a. And now we're basically done. We can rewrite that as integral a to x dy, p plus x minus y q minus p prime u plus x minus y r, and we close that, and then we have plus x minus a times u prime of a minus p of a u of a plus u of a. And so that's basically the solution. We just write this then as f of x plus integral a to x dy of the kernel k of x and y u of y. And now comparing these two equations, we can identify what k is and what f is. And what we see is that k of x and y is equal to p of y plus x minus y q of y minus p prime of y. And the inhomogeneous term f of x is x minus a u prime of a minus p of a u of a plus u of a plus integral a to x of x minus y r of y dy. So that's an example of how you turn a second order ordinary differential equation into an integral equation, and this is what you get. Now I see that most of what I do in class, of course, is in the book, but these solutions are not in the book, and that raises another question: how should I get to you the homework solutions? I don't want to release PDFs of these. Should I just post paper copies on the board outside my office? Would that be? Okay, my office is 3232. Maybe I should write that down. So the is that a good idea, posting homework solutions out there? All right, so I'll do that. So that's basically how one does. In fact, this is one of the more complicated integral equations. Some of them are simpler. And in fact, let me continue with chapter 8. And the next topic is a bunch of definitions, and I think we can just look at the screen here. These are associated with Eric Ivar Fredholm, who lived until 1927. So his most complicated, well, of the set that I'm considering, most complicated integral equation is of this form, which is the form that we have here, but with x equal to b, and with the upper limit equal to b. So you have a kernel, the unknown function, an eigenvalue lambda, u is an eigenfunction, and f is an inhomogeneous term. So this is said to be an inhomogeneous Fredholm equation of the second kind. It's inhomogeneous because of f, and it's of the second kind because it has a lambda u appearing. If you set f of x equal to 0, then you then have a homogeneous Fredholm equation of the second kind. And then if you set lambda equals 0, you have an inhomogeneous Fredholm equation of the first kind. Or if you set f of x equals 0, you have a homogeneous Fredholm equation of the first kind. And of course, the trivial solution is just u 0, but you're supposed to look for more complicated solutions than just u of x equals 0. Now, the Volterra equations were invented just a little bit later, and they're actually special cases of the Fredholm equation, because if you set the kernel in the Fredholm set equal to a Heaviside function times an arbitrary kernel, say, where, of course, the Heaviside function is something that vanishes for negative argument and is 1 for positive argument, then all the Fredholm equations turn into Volterra equations. But let me just go through the litany of Volterra equations. So the most complicated one is of the form that we just derived. Namely, it's a Volterra equation of the second kind, an inhomogeneous Volterra equation of the second kind, where u is an eigenfunction, lambda eigenvalue, and f the inhomogeneous term. If f is 0, then it becomes a homogeneous Volterra equation of the second kind. If you set lambda equals 0 but keep f, then you have an inhomogeneous Volterra equation of the first kind. And then if you drop both the u term and the inhomogeneous term, you have a homogeneous Volterra equation of the first kind. So that's this. These equations are all linear, and of course the implication of linearity is that you can often add solutions. In particular, if you have a bunch of eigenfunctions of the same eigenvalue, then you can take linear combinations and you get an eigenfunction of the same eigenvalue. Also, if you look at the inhomogeneous equation of the second kind, then what you see is that the difference of two inhomogeneous solutions is a homogeneous solution. So you can say that any inhomogeneous solution is some other inhomogeneous solution plus the general solution of the homogeneous equation. And so that is this equation, that the general inhomogeneous solution is a particular inhomogeneous solution plus a linear combination of all the homogeneous ones, but homogeneous with the same eigenvalue. And there may only be one or two that are eigenfunctions with the same eigenvalue. In fact, there might only be one if it satisfies the boundary conditions. Okay, I think I'm going to skip the section on numerical solutions, but if you want, I'll go through it. It's basically that all these equations, if you replace the integral over y, in fact, if you just go back to, what is it, Riemann? Was it Riemann? Yeah, Riemann's original definition of the integral, this would be a limit of a sum, right? dxy, you just evaluate this at various values of y, and then you just you try to solve it at discrete values of x, then these all become matrix equations, and you can use some of the ideas of chapter 1 to solve these. And of course, the linear algebra is extremely well suited to digital computation, and so you can do remarkably complicated problems with remarkably complicated problems in linear algebra can be done almost instantly on an ordinary laptop. Now, there's an aspect to integral equations that's quite interesting from a somewhat mathematical point of view. By the way, in this classroom, we're apparently on Eastern time, Eastern Standard Time. It's really 5:56. The clock says 7:56. Anyway, so let's suppose we have a second order linear homogeneous differential equation, and of this form, where L is a differential operator, and you might think that C has hidden in it an eigenvalue, possibly even a weak function. No, C actually, I wrote C there as a constant, so let's leave it as just there it's effectively an eigenvalue in a sense. So, what one can do is choose a kernel to write the solution as an integral over another complex variable along some contour. And what you typically do is the contour has two endpoints typically, and you arrange that at the two endpoints, I guess we call this a kernel. The kernel K vanishes at the two endpoints. That'll just make things easier. And but then once you've done that, if you can find a differential operator M, to put it differently, if we now write U like this, then the equation LU plus CU equals 0 then becomes this integral equation, where you integrate along the contour. L acts on the kernel, it's acting on Z, and then the kernel is a function of Z and W, and we're integrating along W. The next step is the non-trivial step, where you look for a linear operator M acting on, involving W derivatives, such that M on the kernel acting, differentiating with respect to W, gives you L, which has Z derivatives on the same kernel. And if you can do that, then what you find is that this becomes a simpler equation. In fact, it can be a much simpler equation, because you now have an equation, some differential operator acting on W, acting on K, plus C, K, all this acting on V, and all it has is W derivatives, and you have a contour. So what you can do is you can integrate by parts, integrate the W derivatives by parts, and then if you've chosen K so that it vanishes on the boundary at the ends of the contour, you don't have to worry about the boundary terms. And often, what you've got after you integrate by parts is you have a differential equation in W that is much simpler. And we'll see an example of that. We also have seen in earlier chapters examples of this that seemed, that show you the utility of you writing unknown functions as contour integrals. In particular, it's often useful to write the unknown function as a Fourier transform of something else, or as a Laplace transform of something else, or if you have, if you write K of Z and W as Z minus W to the power A, well, this is this is called Euler's kernel, and it occurs in Cauchy's integral theorem, Cauchy's integral formula. So this trick isn't as strange. It seems strange the way I presented it, because you imagine some horrific contour in the complex plane, but you see this contour can be something very simple. In fact, it's normally just straight lines. And in fact, in these two cases, it's just one line is along the real axis, and the other one effectively is just off the imaginary axis. And in Euler's case, it's whatever you want. An example of this is Bessel functions. And Bessel's differential equation is this, and the differential operator L is given by 839, and the constant C is minus lambda squared. So, and by the way, the Bessel functions, there are many kinds of Bessel functions, but the two that we'll study, a couple of weeks, there are the cylindrical Bessel functions and the spherical Bessel functions. The spherical Bessel functions are quite simple, but the cylindrical Bessel functions are really non-trivial functions. They're well, let me not characterize them, but what we're going to do now is write Bessel functions as contour integrals, and so the contour integration is a price to pay, but what you get as a dividend is you don't have to actually have the infinite series for the Bessel function, which is just a very complicated infinite series. So what do we want? We want a differential operator M and a kernel K so that Mk is equal to Lk. And so what we want is the second minus the second derivative with respect to W of K should be this expression, namely L acting on K, and L is z squared d by dz squared plus zd by dz plus z squared. And I'm, of course, using subscripts to indicate differentiation. Well, it turns out that the solution, or a solution, is e to the iz sine w, and you can have a plus or minus sign in the exponent here. And that's a solution that's entire in both z and w. And in terms of it, the integral equation then obviously is this form, which is what we'd expect. And the remarkable thing then is that once we've got the integral equation in this form, we can integrate by parts once. And if we integrate by parts, what we get is this. And if we integrate by parts a second time, we get this. And this then is a boundary term. But that boundary term typically vanishes at both ends. And so the solution is just k times v double prime plus lambda squared v has to be 0. But that's just this differential equation, which is a trivial equation to solve because it's just v is equal to e to the I lambda w, or e to the minus I lambda w, if you want. And so this is quite amazing. It means that you can write essentially arbitrary Bessel functions as contour integrals of this form, and the v function is then e to the I lambda w. The kernel is here, and so you just have to integrate this along this contour. And so then you pick a contour so that this thing vanishes, so that k vanishes at both ends. And in fact, what you want is not only k to vanish, but the w derivative of k should vanish, and vanish sufficiently strongly that even when multiplied by b, it's still 0. The solutions are called the Hankel functions, or Hankel functions, of the first and second kind, and they are distinguished by just what the choice of contour is. The first one, so let's see, I guess where was the definition of the first contour? Okay, the first contour runs from minus I infinity. So let me show you what this looks like. So C1 goes from minus I infinity up the imaginary axis to the origin, and then down to minus pi, and then up to minus pi plus I infinity. So this is called C1. And that gives you the first Hankel function with an index lambda, where lambda is that eigenvalue there. The second one is an analogous contour. It runs from pi plus I infinity down to 0, and I'm just wondering if I made a mistake here. To pi, sorry. Then over to 0, and then down to minus I infinity. So if we draw them on the same graph, the first one goes like this, the second one goes like that. And this is pi, and this is pi plus 9. So this is C2. So, now of course, these contour integral expressions for the Hankel functions are useful for some properties, not for other properties. It's always true that you can any given expression or mathematical step that proves some things makes others worse frequently. In any event, one thing that one can show from these is that H1, if lambda is real, H1 is the complex conjugate of lambda 2 if Z is positive and lambda real. So that's one thing that one can show. What I don't know, would you like me to show you why it is that this actually is a solution? In other words, let's see, why don't I go over here? So what I'll do, I think I will show you this. And I'm looking for an ordinary eraser. So what we want is an equation. So what we have is z squared kzz plus z kz plus z squared k plus kww equal to 0. That's what we want to show. So let me just remind you that that's what we want to show. In other words, we want, if you take the left-hand side and just add it to the right-hand side of 840, you see this is the equation we want. And now what we've got is, let's compute this. And so if we compute this, what we get is minus z squared sine squared w times k plus or minus iz sine w times k plus z squared k minus z squared cosine squared wk plus or minus iz cosine w, the w derivative of that times k. And these two terms obviously give you minus z squared. And so we have minus z squared k. This term is plus or minus iz sine wk. And we have plus z squared k here. And the derivative of this, of course, is minus sine w. So this gives you minus a plus iz sine w k. So the whole thing is 0. So that's, I think that's enough for chapter 8, but if somebody has a question, maybe we could think about what the answer might be. All right. Okay, so let me now skip to the chapter on Legendre polynomials and spherical harmonics. And this is closer to the content of most physics courses and physics books than the chapter on integral equations. And the first thing to notice is that the monomials x to the n span the space of functions that have power series expansions around the origin. And so the power series expansion is like that. And these functions xn are complete, but they're not orthogonal and they're certainly not normalized. And so what Legendre did was define a set of polynomials that are orthogonal and are normalized. So he imposed the condition that for different, when n is not equal to m, the thing should be 0. And the other condition he imposed to get the orthogonality is that Pn x to the m should vanish if m is less than n. M and n are both integers. And he also imposed a normalization condition that at the right end of this interval from -1 to 1, all Legendre polynomials are unity. And so on the cover of the book, of course, is a graph of the first. I don't remember how many I made the graph, actually. Sent it to Cambridge. So what we want to see is we want to figure out what these Legendre polynomials are, and so we write them as an nth order expression, an nth order polynomial. Here is actually a graph of the first 20 Legendre polynomials. P0 is just the line at the top. P0 is just 1, the number 1, and then P1 is just this line that goes from P1 is just x, so it goes from -1 to 1, and then the others are more sophisticated. And MATLAB made that graph. Because when I said I made the graph for the cover, it's actually MATLAB that made the graph. Code to MATLAB. So what we want then is for these coefficients to be chosen such that we obey, so that the nth Legendre polynomial is orthogonal to xm for all m less than n. And that gives you this linear equation. And we then also have the normalization condition. And so this is a sufficient number of conditions to determine all the constants, the n+1 constants. This is n conditions up here, plus 1 condition there, so it's n+1 equations for n+1 unknowns. And these if you then use these conditions plus that condition, you can then figure out that P2 is 3x squared minus 1 over 2, and P3 is 5x cubed minus 3x over 2, and so forth. And of course, MATLAB or Mathematica or Maxima, I guess Maxima can do it, right?
Might be able to.
Can give you, well, it certainly can if you use Rodrigues' formula. So Rodrigues, who lived until 1851, invented a very nice formula for the Legendre polynomials, namely just an nth derivative of a rather simple function with suitable normalization. And then if you write x squared minus 1 as x plus 1 times x minus 1 and use Leibniz's rule, you can rewrite it as this. And then if you set x equal to 1, you see that all these terms vanish, so only one term survives. And you see that Rodrigues got the normalization right. You can then check that these formulas are, that Rodrigues satisfied the orthogonality condition. And the way you do that is you want to show that x to the mpn integrated from -1 to 1 is 0 if m is less than n. And what you do is you use Rodrigues' formula, and then you integrate by parts n times, and you notice that the function x squared minus 1 vanishes at x equals -1 and x equals +1, so all the boundary terms vanish, and the integration by parts just takes you smoothly to this, and then obviously if m is less than n, this thing vanishes, so you get 0. So that shows you that Rodrigues' formula is correct. And one can also show, in fact, let me use the bottom of this board to write it down, although it'll be on the next slide, so I don't know why I have to write it down. Namely, that the orthogonality relation is that the integral from -1 to 1 of Pn with Pm is delta Nm times 2 over 2n plus 1. So it's a very nice and simple formula. One of the things that always fascinates me is these generating functions. And the generating function for the Legendre polynomials, in fact, turns out to be this function g of t of x, which has a geometrical significance that's very important in physics, namely it shows up in 1 over the distance between 2 points in 3 space. And that, of course, is your electrostatic formula and your Newton's gravitational formula. In any event, what you see here is that if you write the generating function as a sum t to the n times little pn of x, you see that little pn is the nth derivative at t equals 0 of this generating function. It's obviously a function just of x, and you can show that it's a polynomial of degree n. And we can actually figure out what they are by this elegant sort of trick. Namely, you integrate the product of the two generating functions for different values of t, and v, say. You integrate from -1 to 1 on x, and that turns out to be this expression here, and this is an exact answer, namely it's a logarithm of a ratio, and then the logarithm formulas, logarithm of 1 plus something has a nice expansion like this. Those expansions are quoted in, I don't know, the chapter on infinite series earlier in the book. And so now you just rewrite this in terms of the right-hand side, namely the PNs and VN, PN and PM, TN and VM. And so we now see that this has to equal that. So we have this expression. But this is an infinite sum of, this is an identity in T and V, and here it's TV to the K, so that means that this has to vanish when n is not equal to m. So these little p's are orthogonal to each other. And it's then, and in fact, you then get this, you not only do you find that they're orthogonal, but that this is the orthogonality relation. And if you set x equal to 1 in the original expression, and in other words, the original expression was this expression with little p's in it. And so if you set x equal to 1, this becomes 1 minus 2t plus t squared. That's 1 minus t squared. And so the square root of that is 1 minus t. And that has to be equal to, that's obviously equal to the sum t to the n for t less than 1. And on the other hand, by the right-hand side here, it's little pn of 1, tn, t to the n. And so that shows you that pn of 1 is equal to 1. And so these little pn's are the big pn's. These are the Legendre polynomials. And we can now write the Legendre polynomials in terms of their generating function like this. And let me just flash this. I don't think we need to go through in detail because we've seen the Green's functions for Poisson's equation several times, namely 1 over 4 pi r, big R minus little r, say, and that then is this square root here. That's the Green's function for minus Laplacian on g gives you the delta function. And if you set x equal cosine theta and the angle between r and r prime, t equal to little r over big R, you can then rewrite that in terms of the generating function 1 over big R. And then you then get the expression that this Green's function is 1 over r times this sum. And that's something that occurs in many places in physics. So Legendre's differential equation, I don't know, this is just a matter of keeping track of things. So basically, Rodrigues' formula says that the Legendre polynomial is proportional to the nth derivative of this expression here. And if you take the first derivative of u, you see that it's 2x squared minus 1 to the n minus 1. So multiplying both sides by x squared minus 1, we get this equation here. And now what you do is you use Leibniz's rule to differentiate both sides of that equation n plus 1 times, and what you get is that, and then this, and then, well, let me just say you eventually get Legendre's differential equation. In fact, you get it in self-adjoint form. This differential operator, as I said, is formally self-adjoint. The function p is positive on the open interval, vanishes on the endpoints. So Legendre's differential operator, his differential equation, the domain D of functions that are twice differentiable on minus 1 to 1, form a singular self-adjoint system. Singular because p vanishes at the endpoints. The Legendre polynomial is an eigenfunction of L with eigenvalue nn plus 1. The weight function is wx equal to 1, and the orthogonality relation, well, an earlier orthogonality relation that we derived for self-adjoint systems in general tell us that the eigenfunctions of a self-adjoint differential operator that have different eigenvalues are orthogonal on the interval. When integrate it with respect to the weight function. The weight function here is just unity. And so once again, we recover this orthogonality, which we already arrived at several times. These eigenvalues nn plus 1 increase without limit, so that means that the Legendre polynomials are complete, and so we can use them to represent the delta function. And what I did here was compute the first 10,001 terms of an expansion. The expansion is just below here. There's the expansion, delta x equal to the sum of 2n plus 1 over 2 pn of x prime. This being the, this is basically 1 over the eigenvalue. And since we have a delta function there, what we can do is we can multiply both sides by f of x prime, say, and integrate over x prime. What we get is f of x then is this integral, and that gives us this integral. This is called a Fourier-Legendre expansion of the function f of x. In physics problems, we sometimes use x, but we often write x as cosine theta, and then d by d theta, of course, will be d by dx multiplied by d cosine theta d theta, or minus sine theta d by dx. And that means that Legendre's equation in these form, and this expressed in terms of theta, well, d by dx then is minus 1 over sine theta d by d theta, and then Legendre's equation takes this form. And this is the form that one sees it frequently in elementary books. One typically sees that formula in books elementary books on electrodynamics. There are various recursion relations. In fact, there are a million relations involving Legendre polynomials. I just wrote down a couple of them. If you take the t derivative of the generating function, you get this expression here. You can rewrite that as this. You then equate coefficients of t to the n, and you get this recursion relation. And you can use it then to generate the Legendre polynomials. In fact, this is probably a faster way of doing it than using Rodrigues' formula, because if you have Pn minus 1 and Pn, that gives you Pn plus 1 almost immediately, and so then you can generate them all in that way. Another thing you can do is take the x derivative of the generating function and massage that equation, and again you equate coefficients of t to the n, and you get that equation 942, and so that's a recurrence relation. And if you combine that with the combine 937 with 942, you get 943, and then you can get 4 more recurrence relations. And you can then rederive Legendre's equation in self-adjoining form. So I feel free to study those in detail, but I don't think we need to do them in detail in class. there are special values of Legendre polynomials, and we know that at 1, when x is 1, they're all unity. At x equals -1, they're also rather simple, namely Pn of -1 is -1 to the n. And the way you see that is you just set x equal to -1 in the generating function. That gives you 1 over 1 plus t. That's the sum of minus t to the n. And but that also has to be Pn of -1 t to the n. And so Pn of -1 is -1 to the n. And the generating function is also even under reflection of both variables, so you get this expression. And so that tells you then that Pn of -x has to be -1 to the n Pn of x. So what does that tell you? That tells you that the nth Legendre polynomial is odd if n is odd, even if n is even. And I guess that's something that we could have noticed from Legendre's equation when we get back to the differential equation. Right, well there's the equation right there. What you see here is that the differential equation is 1 minus x squared times the second derivative with respect to x on Pn. So the second derivative is an even differential operator, 1 minus x squared is even. And then the other term is a first derivative of Pn and minus something that's linear in x, the derivative of minus 1 minus x squared. And so that's the product of two odd functions. That's also even. And then, of course, we have the rest of it is just 1. 1 is even. So that's why, so the differential operator is even, and that's why you get solutions that have definite parity. Some of them odd and some of them even. This also tells you that if you set x equal to 0, then you have Pn of 0 is -1 to the n Pn of 0. If n is odd, Pn of 0 has to vanish. So the odd Legendre polynomials vanish at the origin, and in fact that's why if we flip back to this original graph, we see, blow it up just a bit. Blow it up a little bit, you see that a lot of the functions are going through the origin at 0. Those are the odd ones. The even ones don't. And you can see that the ones that don't are even around x equals 0. They go down, or they go up. I find this graph somewhat fascinating, actually. All right, so let's see, where were we? We're looking at equation 15. So with a little more effort, you can also show that the even functions at 0 are given by this expression. So are there any questions? Remember, you get candy if you ask questions. Now some of these formulas for the nth Legendre polynomial involve pretty big factorials, and when n is big, the question is, what do you do? Compute, n factorial for NP is really, really, really huge. And so an expression that I found on one of the NIST web pages was that as n goes to infinity, for absolute value of x less than 1, Pn of x is the square root of the arc of cosine divided by a quarter power of 1 minus x squared, an arc, and then it's the simplest cylindrical Bessel function of argument n plus a half arc cosine of x. And that's not an obvious and simple relation. And you can also say that, you can also show that it's approximately equal to this. So these are things you can do if you need to approximate Legendre polynomials numerically at huge values. Schlaefli used Cauchy's integral formula and Rodrigues' differential formula to write the Legendre polynomial as a counterclockwise integral around x, and so you're integrating dz prime. I could have just used dz. I don't know why I had a prime on that. So let me. So that's an expression. Now, once again, you might say, why would anyone do this? Well, this expression can be used to prove other things. And so that's the way it often is in mathematics, and sometimes in physics. You sort of take one step back and get something rather complicated, but that allows you to take a different step forward in a different direction and derive something. Now, Rodrigues' formula, I don't know how far he went with his formula. I think it's very likely that he realized that his formula could be generalized. He probably did generalize the formula to create a whole family of orthogonal polynomials. And the way you do that is you define your nth order polynomial R sub n as some q to the n of x times a w of x, an nth derivative, and then you derive by just a normalization factor, e sub n. You want them to be orthogonal with respect to the weight function w, and in fact, they automatically will be orthogonal as long as q vanishes at the endpoints. So that's quite cute. So in other words, so I use R for Rodrigues as the generalization. I think this is very, very nice that we have a formula here. Pick an arbitrary function q, an arbitrary function w, just choose the e's so that things are appropriately normalized, and you get, bingo, a formula of orthogonal polynomials as long as you get q vanishing at the endpoints. And anyway, so that's quite nice. The examples are some very important polynomials, or the Jacobi polynomials. Their q of x is very much like the Legendre choice, x squared minus 1. But you use a different weight function w, and your normalization is 2 to the n factorial. And for alpha greater than minus 1, beta greater than minus 1, you wind up with these Jacobi polynomials, which are orthogonal on this interval and satisfy a certain normalization condition and a certain differential equation. And it turns out that that their generating function, in terms of the generating function for Legendre polynomials, is given by this expression here, which is, again, pretty remarkable. If you set alpha equal to beta, you get the Gegenbauer polynomials. And if you set alpha equal to beta equal to plus or minus a half, you get the Chebyshev polynomials of the first and second kind. And if you go all the way to alpha equal beta equal 0, you go back to the Legendre polynomials. You also get the Harmonic polynomials, Hn, and that's the nth derivative. This is, the weight function is e to the minus x squared, but you're just using q of x equal to 1. But now you're using a different interval. The interval is minus infinity to plus infinity, and things are vanishing because of the weight function, not because of q of x. And so you've got then the Harmonic polynomials, which have this orthogonality relation and satisfy this differential equation. They have this generating function. Then there are the Legendre polynomials, and these occur in the case of the hydrogen atom. Legendre polynomials are q of x equal to x. What could be simpler, apart from q of x equal to 1? You then set w equal to x to the alpha e to the minus x. Your Legendre polynomials are given by a Rodrigues formula like that. They're orthogonality in this way. They're orthogonal in this way. They satisfy this differential equation, have this generating function. And the non-relativistic hydrogen atom wave function with quantum numbers n and l, the radial one, is rho to the L, the Legendre polynomial 2L plus 1 sub n minus L minus 1 of rho, and then e to the minus rho over 2, where here rho is 2r over n times the Bohr radius. So I think we can stop here, both because we're out of time and we're at a natural place to stop. I wish you guys would ask more questions. I think you'd learn more if you ask more questions. Okay, you might as well stop it.